Hey there, back already? Hungry for another slice of physics? Well, you're lucky. I've got one ready for you, and this one is topped with an example problem of motion with constant acceleration. We're going to take your car for a speed test on the racetrack and figure out various components of motion while you're driving it. Okay, here's the specific problem we are looking to tackle today. In this example, you take your car to the racetrack for some speed tests. You start from rest and floor the gas pedal, speeding down a long, straight road. It takes you exactly 4.5 seconds to reach a speed of 60 miles per hour. That's the information given, and the two questions are, what's your acceleration in SI units, and how much distance did you travel down the road? It's asking you to make the assumption that the acceleration is uniform during this ride, which is quite acceptable. For almost an entire 4.5 seconds, you had the gas pedal floored completely, so the car would be accelerating at the same level. The first thing I want you to do as you work on physics problems is, as you read them, underline some important aspects. So the information that seems to be valuable here is that it tells you that you started the car from rest. That gives you some idea of the initial velocity. And the long straight road tells you that there is no change in direction, so this is just one-dimensional motion of the kind we have been dealing with so far. Then it gives you the time duration. It tells you that you went for 4.5 seconds and you reached a speed of 60 miles per hour. That gives you the final velocity. And it's asking you for the acceleration, and it's asking you for the distance or displacement of your motion. Okay, once we've done that, the next thing to do is draw a pictorial representation of what's going on here. Once again, I'm not a good artist, so a lot of these pictures will be just dots for me rather than pictures of cars. So let's say this is your starting position where your Vxi was 0. I've assumed that we are moving in the x direction horizontally. And then you speed up, so if I were to show some of your velocity vectors, they will look like this. It's going faster and faster. And you reach this point over here, and by the time you reach that point, your velocity Vf or Vxf is 60 miles per hour. Okay, once we've done that, it's a good idea to list all the things we know and all the things we need to find out. I've already got Vxi here listed at 0 miles per hour, which is also 0 meters per second. The reason I'm working with SI units is because that's what was asked. Vxf is given to us as 60 miles per hour, which we can convert to meters per second. And that's a preliminary calculation that's good to do before we even worry about solving the problem. And since you know how to do that unit conversion, I'm not going to do it over here again, except to say that that is 27 meters per second. So I got my initial velocity, I got my final velocity, both are in the positive x direction. And the next thing that was given was the duration of 4.5 seconds. I can write that in my notational form as delta t equals 4.5 seconds. And what's being asked for is the acceleration and the displacement. So once I have got this level of understanding of the problem, and only after I've got this level of understanding of the problem, should I look at equations. So here are my 4 equations for constant acceleration motion. And guys, I'll just say it one more time. Please avoid the urge to read a question and look for an equation immediately to plug things into. That often leads you in the wrong direction. It is really important to set up the problem this way before you look at equations. So once I have done this, I know Vi, I know Vf, and I know delta t. So the equation that is most useful is this one, and the second equation is just another form of that, so I could have used that as well. So the acceleration is simply delta V over delta t, and in our notation that'll be delta Vx over delta t for Ax, which is Vxf minus Vxi over delta t. And now it's just a matter of putting in those values and letting your calculator do the job. I've got Vxf of 27, Vxi of 0, delta t of 4.5. And since the velocity is in meters per second and the time is in seconds, This will give me an acceleration in meters per second squared, and your calculator will tell you that that's simply 6.0 meters per second squared. So there we have it. That's our first part of the answer. And if we want to be, and because it's also a positive value, this tells us that the acceleration is towards the right, same direction as the velocity. The last part was to find the displacement. I want to get delta x, or displacement, which is given in a straightforward way by this equation over here. So now I can put in Vxi times delta t plus 1/2 ax times delta t squared. And when I plug in the values, this is 0 times 4.5, which will be 0, plus 1/2. Now I got my acceleration that I just found out, so I might as well use it. I got 6.0 times 4.5 squared. And the units now would be meters per second squared times second squared. So the second squared cancel, and I get my answer in meters. And this gives me a value of 60.75, or down to our two significant digits, 61 meters. So what this is saying is that the acceleration that you're moving with while you had your car floored was 6 meters per second squared in SI units, and the distance you covered is 61 meters down that straight stretch of road, which is about 200 feet. That makes sense. That takes care of this problem. We have solved it. Okay, just to get a little bit more practice, let me present you with a second part of this question. Now it says, wanting to go a lot faster, you maintain the same acceleration for 6 more seconds. So that's a key piece of information here, 6 more seconds, so that's delta t. And the fact that we have the same acceleration is relevant as well. And it's asking now for what is our final speed at the end of that 6 seconds, and how much total distance do I travel. And the total distance means that I want the distance for the first part and the second part. So following our steps here, I keep accelerating, and eventually I reach a point over here. And I'm going to use a different color for solving this so you can separate the two things. So let's call this Vxf. This is the final speed for this motion that we are considering now. So let's start listing some of the things we have for this motion. I've got Vxi no longer as 0 because now my motion that I'm considering is between here and here, which took 6 seconds. So Vxi is the 60 miles per hour, which is 27 meters per second. I have delta t of 6.0 seconds. I've got acceleration, ax, of the same thing that we found out before, 6.0 meters per second squared. And it's asking for Vxf. Now we can use the second equation over here to solve for this. And so that simply is Vxi, which is 27 meters per second, plus a times delta t, 6.0 for a, and another 6.0 for delta t. Meters per second squared here times seconds here. One of the seconds would cancel, and the answer for this part would also be meters per second, which will add up to the 27 to give me a Vxf of 63 meters per second. And just for your information, you could convert this backwards to miles per hour, and that'll turn out to be about 141 miles per hour, which makes sense. If I've got my gas pedal floored for that long, I would reach those kinds of speeds. So there's my answer to that first part. And my very last question was, how much total distance have I traveled? There are two ways to do this. I could figure out the distance traveled for just the second part and add it to the distance that I already know for the first part. Or I could take the entire motion as one motion, and then for that, use the appropriate initial and final values. I'm going to choose to just work with the second motion here and then add finally to that first part. So for this one, I've got Vxi times delta t, back to this third equation, plus 1/2 ax times delta t squared. And this will give me 27 for my initial velocity of this segment times 6.0 plus 1/2 6 for acceleration times 6 squared for time squared. And all of that in your calculator will give you 270 meters. And I'm quite not done yet. So my final step is this delta x total would be the delta x for the first part and delta x for the second part, which would be 61 plus 270, which would give me a total distance of 331 meters. And that's my answer to this last question here. So I hope this slice of physics satisfied your hunger for solving physics problems like this. See you later.